right, so this concept, it's going to be something we use in almost every chapter of this textbook. It will just pop up every, maybe twice in every chapter, okay? As sections, or parts of sections. So it's important that we learn it now, so when we get to, section 5, 6, we don't have to spend an entire day coming back, revisiting, relearning this stuff, so we can address 5, 6. Because if we do that, as many times as it shows up in this course, we'd be wasting probably around 20, 21 days, okay, by revisiting and reteaching something, which we cannot do, all right? So we need to learn this. Also, it's going to be something that goes on Algebra 2. You talk about distance and use distance in Algebra 2 in my college algebra students, my pre-calculus students. They were using it last week, okay? And we're going to keep using it with them the next couple days. So it's something that this year is going to come back to us. Okay, we'll leave it for a couple days, it'll come back. We'll leave it for a couple weeks, it'll come back. We'll leave it for a month, it'll come back. And then it comes back to that class as well. But the better we understand it now, the easier it'll be to address when it does come back. Okay? We'll talk about how we measure segments. And I'm going to kind of skip ahead a little bit in the PowerPoint to slide 5, and then we'll go back to slides 2. And I got the order of this PowerPoint I'm not real fond of right now. All right, so what allows us to develop essentially a distance and create a numerical representation of a distance is what we call the ruler postulate. Okay? The ruler postulate, okay, essentially says every point on a line can be paired with a real number. And it says this makes what we call a one-to-one correspondence between the points on the line and the real numbers. And what we mean by one-to-one correspondence is that every single number that you can come up with, okay? So if I gave you just a pencil and a piece of paper, said write a number down. Any number you ever write down, as many characters as long as you want to make it, put your decimal point anywhere you want to put it, that number has a point on the real number line. Okay? What also exists in this phrase is that every single point on the number line can be matched to a number. So every number gets a point, and every point gets a number. Does that kind of make sense? And that's what we mean by one-to-one correspondence. Okay? And what that allows us to do is develop essentially a ruler or a measuring device. Okay? It says the real number that corresponds to a point is called a coordinate of a point. It's a vocab word. But when we talk about real numbers, you guys know we've done this before. It's a component to Algebra 1. You've got a grouping of numbers. Okay? And we actually have several groups of numbers. Maybe the first ones that you're most familiar with are maybe your natural numbers. Numbers like 1, 2, 3, all the way up to infinity. Okay? So those are your naturals. You don't need to write this down. We'll see this many times. Those are your natural numbers. Then you have your whole numbers. Your whole numbers start at 0 and go through infinity. 1, 2, 3, 4, 5. So essentially your whole numbers are the same thing as your naturals. You just include the value of 1. Okay? But if I do that, and I try to create a number line, right now all I've got, guys, is like 0, 1, 2, 3, 4, all the way to infinity. There's a bunch of gaps, right? There's a bunch of numbers that I don't have highlighted, I don't have listed or identified. So that grouping of numbers becomes what we call our integers. So our integers are those numbers. Okay, so we're just kind of creating kind of a Venn diagram here. Okay, and that just gives me my essentially a lot of times your integers are identified as your whole numbers and their opposites. So now we get our number line to go that way, but there's still an infinite number of gaps in there. So then we create what we call our rational numbers. And that's anything that can be written A over B, where B is not 0. A and B belong to, I'm just going to write it this way just to save some room. A and B are integers. Okay? That's what A and B, and that little weird E means belongs to, and there was an element of, and that Z is the generic term that we refer to the integers as. And we'll talk about this stuff later on. But rational numbers start giving me like fractions, right? So anything I write as a fraction, 1/2, 2/3, 5/9, 9/5, that kind of stuff, right? So I start writing all these fractions and I get to fill in a bunch of these spots. And I fill in more and more of these, but I still have an infinite number of gaps, okay? Let's put in something like that. And I still got gaps in that number line, right? And that gap, or those gaps, are things like pi, okay? So pi would be 3.14, right? Goes on forever, never ends, never repeats, okay? So I plug that in, or put that in, and now it eliminates that gap on the number line. Other numbers like radical 2, it's approximately like 1.4 something. Radical 2 fills in that gap. Radical 3, radical 5, radical 6, radical 7. They all fill in a bunch of gaps. Does that make sense? You guys know what those numbers are that don't repeat, or their decimals don't repeat or end, terminate? We had our rationals, and then we have our irrationals. Okay? So we got that group. Okay, the way I remember it is irrational people are kind of crazy people, right? They don't do things that normal people would be doing. Okay? So irrational numbers are kind of like your crazy numbers. They don't do things like the other numbers do. So those are things like pi, radical 2, e. We'll get to what e is later on. But those are your irrationals. If I take all of these, okay, which all of these here, these numbers here, are all subgroups of rationals. Okay? So take all my rational numbers, and think about this, 5/1 is one of these numbers, right? But it's also irrational. Okay, 5/1 can be written as A over B. We group those together. We group the the rationals and irrationals, and it gives us what we call our real numbers. Okay? And our real numbers then is the entire number line without any gaps in it, no holes. So I go from number to number to number to number and never break my number line. Does that make sense? Okay? So that's what I mean by that phrase up there, real number. And we need to, at some point, come to terms with that diagram and that understanding of those values and which ones are which and what groups they belong to, because there will be theorems and postulates down the road that say this statement only works for maybe integers. This statement only works for irrational numbers, something like that. And we got to pay attention to the groups of numbers that we're allowed to work with. This is allowing us to work with all the numbers that we can imagine right now. Is that okay with everybody? Okay. But what this allows you to do is develop a system for finding distance. Every point has a number, every number has a point. That builds a rule. Okay? If I want to find the distance between 2 points, that last paragraph there describes how I do that. Okay? Remember, the coordinate is the number that's associated with a point. So I take the coordinates of both points that I'm using as an endpoints, and I simply subtract them and then take their absolute value. Okay, so I'll give you an example here of what I'm talking about. Keep losing my yardsticks. All right, so I call that point A, that point B, and those are the names for the points, okay? What your text and most texts will do is they'll say lowercase a and lowercase b are representative of their coordinates, the number that's associated with them, okay? So if I were to give you guys a yardstick or a tape measure or a ruler, I told you measure that line, most people, correct me if I'm wrong, would do something like this. Where they would put that number on one of your endpoints. What number am I using right here as the end of my ruler? 0. So most people would say that coordinate is 0, and if you can see up here, this coordinate right here is 22.
Football number.
Huh?
Football
It
number.
is? Okay.
Just letting you know so you make a sign.
All right, I will.
No, you won't. Don't lie to me.
But I tell you what the sign would say.
Alright. You won't make one now.
All right. So that's one coordinate. That's the other coordinate, right? That formula up there says to find the length of this, you would take that coordinate minus that coordinate, take the absolute value of their difference, and you get 22. Well, why do we do it that way? Why do most people associate one coordinate with 0? Is because subtracting 0 is pretty easy, right? Okay, it doesn't get any easier in regards to subtraction than that. Okay? Now the reason we have to do absolute value is because there's never really a defined order that we have to do this. I can go 0 minus 22. That gives me negative 22, but distance always has to be a positive number. And the absolute value function is a tool that will transform any number into a positive version of that number. Okay? Now here's the thing. This is what the ruler postula does for us. 0 doesn't have to be your starting point. Okay? I can put my ruler up here, and let's say I put it on 9. So I let A be 9, and I come over here, and B ends up being 31. So now if I do A minus B in the absolute value, so it'd be 9, A is 9, B is 31. Does this still give me 22 as the distance? Yeah, okay. So you don't always have to use 0 as one of your endpoints. To find the distance between 2 points, you subtract those coordinates, and then you make sure through the absolute value that you always take the positive version of it. Okay? Because distance always has to be positive. If I travel to school today, did I travel negative 5 miles?
Yes.
No, you can't do that. Okay? So I travel positive miles, positive distances all the time. Okay? Is that something we can do? All right. Thinking about kind of showing that again here. And I'm going to zoom out. The one thing I want you to be cautious of, because I'm going to zoom out pretty far. What a lot of people want to do. Let me give you an example. I guess zoomed in first. Okay. So right there, zoomed in, I've got every integer up there from 5 to 23, right? So what a lot of people want to do is say, okay, and this only works because of these integers. Can I count from there to there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It took me 12 spaces to get from where I started to where I ended. And now I know the distance is 12, right? Okay. But if I zoom out, if I change the scale a little bit of my x-axis here, essentially, my number line, and I'm only going by 2s now. This is where people struggle, is that they go, oh, there's 1, 2, 3, 4, 5, 6. That distance from A to B is now 6 units. Is it really 6 units? No, it's still 12, right? It's the way I've set up my scale, my axes, or my number line that gets people in trouble. Okay? So the safest thing to do is always to use the formula. Take your endpoint coordinates, subtract them, take the absolute value. Something I do, and I do this on purpose. I don't know. When I had Miss Coles in high school, so a lot of you had learned the same algebra from the same person that I did. She would always teach something in class and show us shortcuts and stuff like that. But she'd always give the formula, always focus on the formula. Because on tests, she always gave us a handful of questions that you could not do using the shortcut. Okay? I do that on tests now as a teacher. Okay? Because I know people want to use the shortcut, but I also know the importance of the formulas. Okay? So I will give you questions that look like this at some point, where I take the number line out. If I can do this. All right, and I'll say that this number here is maybe like -10, and this one is -8, and this is 0, and that's 12, and that's 200, 210, 300, 471. And I ask you to find the distance between A and B. Are those in chronological order? Is -10 the smallest value up there? And as I move it over, right, should I come across -8 and 0, then 12, then 200, 210, 300, 471, right? They're in order, okay? The spacing or the scaling is wrong, and that's what I want to focus on, because some people are going to count 1, 2, 3, 4, 5, 6, that's 6 units long. Where in actuality, the way I've got it labeled, the coordinate for A is -8. The coordinate for B is 471. I need to subtract those. Okay, I need to go -8 minus 471. Take that absolute value. Okay? So it's going to give me what? -479. It's going to be 479 units, whatever they may be, feet, inches, miles, centimeters, whatever would specify as being the distance that I said. Does that kind of make sense? And that forces you to have to know the formula. You're going to get it wrong if you just count. You've also seen it with slope last year, so I'll give you the same kind of concept here. Let's go back to putting our axes back in here. If I gave you these 2 points for A and B, and you can see here the nice aspect of those points, right? They're integers, correct? So because those are integers, if I asked you to find slope last year, you could count your rise, you could count your run, and you got your slope, right? I changed those order pairs a little bit. And I rounded them to 15 decimal places. Am I going to be able to accurately count the vertical and horizontal movements from A to B there? I should, okay? And if I can, I'm a pretty special person, all right? But the formula will do it for me. Does that make sense? Okay? So that's why I want to address that formula. Because there will be times, guys, where I'm trying to find the distance of maybe that segment right there. Let's see if I can get it back. There we go. Something similar to that. Okay? Where the one point is maybe a nice number like -2, but this point over here is kind of an ugly number like 9.72838. Okay? So we have to be able to use that formula. Does anybody have questions over that? All right. So that's the ruler postulate. As we're using the ruler postulate, this phrase here is pretty important. Okay? You don't need the stuff above. The stuff above we've already talked about. The paragraph there at the initial paragraph that I don't have highlighted is restating the ruler postulate. And this was just to show you another example. But right there where I've got highlights says, in this case, we want to know the length of segment MV. If I ask you segment MV's length, hopefully you tell me it's full. Okay? The way that we asked that, we were told to determine that, is through the use of some special notation. Okay? We're just going to be said, it'll have the words find MV. Okay? So it'll look like this. That's all you'll see. Find MV. Okay? And the way I actually read that is I say find length MV or find distance MV. Okay? So when we have a line, remember when I have a line above it or a symbol above it, I read that as segment MV. And that refers to the shape. Okay? Or the physical object. Okay. When I take that symbol away, when I take that segment symbol away, it gives a whole new meaning of how I interpret it. It now means distance or length. of segment MV. That's what that implies. Okay? Which that is a characteristic that describes segment MV. And it's going to be, let's write down, it's going to be a real number. It's going to be a distance, a length. Might be 12 units, might be 12 feet, might be 137 miles, or something like that. That kind of make sense? Okay? So the removal of the segment symbol now brings to the table the discussion about what a length is, what a distance is of that segment. Okay? So when you see the symbol above, I want you to think, okay, it's a physical shape that I've got in my hands or in my picture. And when I take the symbol off of it, it's just MV. Now you're saying, okay, we're talking about a distance that describes it, or a length that describes that particular shape. And that's important because on the intercourse exam, they're not going to say in English words, find the length of segment MV. They're just going to say find MV. And it's going to be understood that you know what to do with that. Okay? And, I think half the battle in this course is being able to read the notation, understand what they're implying with that notation. Huh? I know. Yep. All right, so that gets us to, so a lot of the questions, guys, that we're going to see are going to, in our homework initially, are going to be pretty elementary, where they give you a segment on top of a number line, and they ask you to find this length, and you simply subtract the endpoints. We've done a couple examples of that now. The other types of questions that we'll see in this section's homework is in reference to what we call the segment addition posture. Once we reduce this, we'll do one example, and then we'll pick up with the rest of this PowerPoint tomorrow. With this posture, then you can remember it and refer to it when I ask questions about, a lot of times I'll ask a question about, like, what is a solution to some question or some problem? Somebody tells me 12. My question will then be, well, why is it 12? And a lot of times your answer will be maybe the segment addition posture. You can say the segment addition posture. Or you could say, because if 3 points A, B, and C are collinear with B between A and C, then AB plus BC equals AC. My thoughts are probably a lot of you would prefer to say segment addition posture, right? Instead of what the phrase says. But we still need to know both. Okay? When we're discussing and talking about them, you're going to hear me say the word or phrase segment addition posture, so you can use that as well. So I'll give you a minute to write that down, and then we'll come back and discuss what it's really getting at and discuss what it's not talking about. All right, so the segment addition posture says if 3 points A, B, and C are collinear, so that's an aspect that we need to know. So that's vocabulary, a vocabulary word from last week. If I don't know what that vocabulary word means, then I'm probably not going to be able to address this accurately. Okay? So those 3 points have to be collinear. B has to be between A and C. Okay? The only time, guys, that I can apply what I've got underlined in purple there, because that's what we're trying to target. That's the principle. The key concept that we're trying to target is that we're going to take AB plus BC and set that equal to AC. And visually what that means think about this. If you're standing right here on A, and you walk right there to B, take a break, and then walk to C. And I ask you, how far did you walk? Did you walk the same exact distance that somebody starting at A walked if they didn't take a stop in the middle? That's what that theorem or that postulate is saying. Is that total distance A to C is equal to the sum of its parts. Okay? Hopefully that's kind of an elementary concept to visualize. But I can only address it in that manner if what I have underlined in green exists for the picture or the situation that I'm dealing with. Okay? So for instance, let's say I have something like that. Does AB, that distance, plus BC, that distance, equate, when I add them together, to that distance? No, they don't. And if we were to measure them, you're going to find out that the red ones added together are much longer than the black one. Okay? And you guys know that the shorter distance between 2 points is always a straight line, right? Well, right there, if I go A to B and then B to C, I've bent myself, right? So I'm adding a little bit more distance than what's necessary to get from A to C. But the reason this doesn't work is because we have not met what I have underlined in yellow, or sorry, green, right? Those 3 points are not collinear, so I can't target the purple information yet. Does that make sense? So the only time I can use the purple information and set up an equation like that is if my stuff that I have underlined in green is met. Okay? And that's true about all if and then statements that we ever come across. The then part is what we're trying to address. It's probably presented something like an equation or a relationship that's important, but it only works if the green stuff is occurring or if the green stuff is true itself for us. Okay? Hopefully you can make that argument that AB plus BC equals AC. So when we get to an example here, I want to look at that segment EG. Okay? There's a point in the middle, F. I'm going to tell you that E, F, and G are collinear. F is between E and G, so this whole thing is satisfied. So I should be able to set up an equation that allows me to address this particular problem and solve for X, and then eventually for EF and FG. The first thing I always want to do with these is develop kind of the general equation for our problem. Okay? So this was the general equation for this picture here, using A, B, and C. But using E, F, and G, take a minute and see if you can come up with a general equation. You know what I mean? There's not going to be any numbers in it. It's just going to be segment distances. Write one down real quick and see if yours ends up matching mine.
You like Michigan?
Huh?
You like Michigan?
No.
Yeah, well, State?
Sometimes.
Maybe sometimes? Well, who else do you like? Alabama.
No.
Do you not like college football?
Yeah, I watch it. I watch it.
NFL more?
I'm not a huge fan. The Buckeyes are all watching.
Who do you like NFL more?
I hate it. More Bears fans that take their lead. NFL is like a soap opera. Okay, so I wrote, and this is the idea that I think about. If I'm walking on E, or standing on E, and I want to walk towards G, I'm going to first walk the distance E to F, right? So that's a distance that I know I've calculated, I've walked through, okay? Distance I've traveled. And then I'm going to walk from F to G. That's an additional distance. So the fact that it's additional is why I'm adding it. So that's the first distance I traveled. Took a break, add to it my second distance, right? And that should equate then as if I started at E and walked all the way through G without stopping. Is that okay with everybody? All right. Now, we can use what we talked about in Algebra 1. You guys remember back to Algebra 1, early on, and this is one of the reasons we take Algebra 1 before geometry, is because you guys did stuff like this, where like they gave you like 2x plus 3y minus z, and asked you to evaluate it if x equals 1, y equals -2 and z equals 3. You did questions like that, right? Well, it's the same idea. But instead of 2x, 3y, and z, we have EF, FG, and EG. Just kind of more explicit, more descriptive variables. Okay? And now instead of like x being 1, now we have EF being that. Does that kind of make sense? So you're going to substitute EF with what it's equal to. Well, we said EF is the same thing as 8x minus 14. Okay? This plus sign is constant. It's part of the equation, so it's going to be there. Now, what is FG? It's going to be 4x plus 1, right? That's what they're identifying it as. And this is where people get in trouble because a lot of times they forget to read the description or the directions, and they're missing a value. Up there, I don't know what by just looking at the picture, I don't have any way of describing what EG is other than what I've already written. Okay? I could say EG is 8x minus 14 plus 4x plus 1. That gives me the same thing on both sides of the equation, which will never lead me to anything useful. What is another way of describing what EG is? It's 59. So we're going to plug in 59 in. Okay? If you at any time go through examples like these or problems like these, and you go through all your work and you get down to 0 equals 0 or something like that, it's because you haven't made your left side and your right side of your equations something different. You're probably missing a description of a segment somewhere that's going to allow you to come up with a variable value. Now you should be able to solve that. It's a multi-step equation. I have my x's. I have my constants. So equal 59. Isolate my variable term. Divide by 12. And I get 6. Okay? So, and this is kind of what I think a lot of times we get programmed to be almost robotic with the things that we do in Algebra 1. 99% of the time in Algebra 1 are just told to solve for x. So right now you've got a year, maybe 2 years of exposure to questions where once you got to x, you were done. You went on the next one. If you did that here, you would be wrong. Okay? Because did the question ask what x was? Or did it ask what EF and FG were? So now we got to take this x equals 6 and plug it back in. So now I'll have 8 times 6 minus 14. What's 8 times 6? 48 minus 14? 34. So 34 is EF. Okay? I want to then do the same thing here for 4x plus 1. So I got 4 times 6 plus 1. And that gives me 25. Now this is a simple thing for this question. Sometimes it gets harder, but we should always be able to check our solutions. We should always be able to somehow manipulate our problem, the values that we have as what we think to be answers, and reproduce something else in the problem. What do I get if I take 34 plus 25? I get 59. Okay? No other number other than x equals 6 will do that for me. Okay? So that's a built-in check that tells me I've done things right. I will show you every time we go across something in this class, a check for any problem that we come across. Because you should be able to turn in a test or quiz or homework assignment knowing whether you got that question right or wrong every single time. Now, sometimes the check might take you twice as long as actually working through the problem did, but you can still do it. And if you can do the checks, it tells me that you got a great understanding of the concept. And chances are you're probably going to be doing things correctly for a while. But that's an introduction to the segment addition postulate. It's an introduction to finding distances. Now that's kind of a basic distance, or sorry, segment addition postulate. We can add multiple things. Okay, so we can do, doesn't just have to be 2 segments. We can do something like this. So we're going to take AB plus BC plus CD equals AD. That little part plus that little part plus that little part should equal the whole thing, right? So however many individual small parts we have or small components we have, we can do that It could also be written this way. You know, can I take AC plus that part CD? Does that still give me the whole thing A to D? Okay. So there might be different ways that you can piece them together, provided how many points you have that are collinear. But you should be able to take small individual components, small individual parts, and add them up to get the whole thing. Okay. What's nice about this, if you understand the segment addition postulate, in about a week and a half, when we get to the angle addition postulate, the same concept, it's the same procedures, it's the segments we use, and okay. So next couple days, we'll continue to work with this, get more practice.